Howdy. My name is Optima.
And my name is Maximum, or Max for short.
You may know us from your previous courses.
In which case, I hope you don't hate us.
You better like us, we are here to help.
Yes, to help make your life less miserable.
You got to love Max's optimistic sense of humor.
No kidding. On an even more optimistic note, network optimization is somewhat less boring than linear programming.
It is indeed one of the most beautiful topics to study.
I agree. Also, I like the fact that we can recycle some of the old introductory slides on optimization.
Let's see what we've got.
All right. We start with the question everyone should be able to answer at some level: what is optimization?
I liked how you called optimization the science of the best the other day, because in optimization we are aiming to find the best possible solution among the feasible alternatives. Our objective is to find a solution that either minimizes a negative attribute of our decision, such as loss, cost, or waste, or maximizes a positive attribute, such as benefit, revenue, or profit.
Next, we continue to a brief historical reference. The origins of optimization are attributed to the 1st century, when the Alexandrian mathematician Hero solved the problem of finding the shortest path between 2 points by way of the mirror. The solution is known as Hero's theorem of the light ray, which became the origin of the theory of geometrical optics.
This highlights the key role optimization played in advancing science from its early days. The solution of a simple optimization problem gave rise to an important theory in physics.
Indeed, the solution is so simple that we can demonstrate it within a minute. So, we have the source of light given by point A, the observation point B, and we need to find the shortest path the light will travel from A to B by reflecting off the mirror.
So, the problem consists in finding the optimal point C on the line representing the mirror that will make the sum of the lengths of the segments AC and CB as short as possible.
Right. At this point I want to pause and let the students discover their inner hero by solving the problem he solved 2,000 years ago.
A great idea that always works.
I'm pretty sure they will figure out that they can find the solution by plotting the symmetric reflection of either A or B with respect to the mirror line.
Let's plot the symmetric reflection of A to be specific.
Sure, let's call it A prime. Then A prime C plus CB is the same as AC plus CB.
So, our problem is now equivalent to finding the shortest path from A prime to B by the way of the mirror.
And since A prime and B are on the opposite sides of the mirror, we just need to draw a straight line between these 2 points and find its intersection with the mirror line.
And it is easy to show that the angle of incidence equals the angle of reflection at the solution point. Nice and simple. What's next?
After this glimpse of ancient history, we fast forward to the 17th century.
This is another great illustration of the major role optimization played in scientific developments. The invention of differential calculus was largely motivated by observing that the tangent line at the points of minima and maxima has zero slope.
And where would our civilization be without differential calculus?
That's a rhetorical question.
Indeed. And how do you like the quote I put on this slide?
Love it. I don't think anyone will have doubts about the practical importance of optimization once they see this great quote of Euler.
I concur with this assessment. The next historical development I would like to highlight takes us forward to the 20th century, when the digital computer was invented.
Makes sense. Computers spurred the development of numerical optimization, because they made solving larger-scale problems possible.
And developing efficient algorithms required serious advances in theory, so computers started the golden age of optimization.
Some of the most significant early progress on both theory and algorithms was associated with solving linear optimization problems.
I find the story of Leonid Kantorovich particularly curious. He was one of pioneers of linear optimization, but because of the Cold War, it took several decades for his achievements to be recognized by a Nobel Prize.
The next breakthroughs in linear optimization were made during World War II, when new algorithms were developed for solving problems arising in military logistics and operations.
This is when the terms mathematical programming and linear programming were coined.
Precisely, because the optimal solutions were referred to as plans or programs, so the name programming for finding optimal programs made perfect sense.
The rise of computer programming a few decades later made the use of this terminology with respect to optimization somewhat confusing nowadays.
That's why there is a push in optimization community to abandon the use of the term programming when referring to optimization theory and algorithms.
That's right, the Mathematical Programming Society was renamed into the Mathematical Optimization Society not too long ago.
But the Society's flagship journal is still named Mathematical Programming.
It may be a little too late to change that one. The journal published too many influential papers.
Anyway, let's move on with your presentation.
Right, returning to the breakthroughs of 1940s, this is when George Dantzig published the simplex method and John von Neumann developed the duality theory.
I'm sure all students taking this course know from previous courses that this material is still of fundamental importance for linear programming.
The golden age of optimization that started around that time is still in full bloom today.
Indeed, optimization is applied to improve processes in virtually all spheres of human activities.
Some application areas listed on this slide are just a tiny piece of a tip of the iceberg.
Today, optimization continues evolving at an astonishing pace. To illustrate this point, our department offers courses in linear programming, integer programming, network optimization, nonlinear programming, combinatorial optimization, global optimization, stochastic optimization, heuristic optimization, as well as several other topics in optimization.
This is indeed a very impressive list, and it is not even complete. Next, I'll let you introduce your favorite topic on this list. You may start by telling your story of obsession with networks. I'll pretend that I hear it for the first time.
My fascination with networks grew out of my passion for coloring books in childhood.
That's a very intriguing start. Tell us more.
It all started when I was 5. I was coloring a map in my coloring book.
This looks familiar. I think I had the same coloring book.
I would be surprised if this map didn't look familiar. Anyway, when I started coloring the map, my dad saw it and asked me to try to color it in a way that no two bordering states have the same color.
That's easy even for a 3-year-old.
Right, but he wanted me to use no more than 4 colors.
Oof. That's tough. Have you done it?
Yes, I have.
Was your dad impressed?
Yes, and he told me that any map can be colored with just 4 colors.
How did he know?
As I learned later, this follows from the 4-color theorem.
Amazing. There are theorems about coloring geographical maps. What a waste of time. I am glad I am not majoring in math.
Don't jump to your conclusions so quickly. The theorem is a lot more general than this, and the map coloring is just a cute example illustrating it for the general public.
So, what are the real useful applications then? Does the humanity really needs mathematicians' help with coloring?
Graph coloring has tons of useful applications, including sports scheduling, timetabling, bandwidth allocation and telecommunications, and many others. You can even use it to solve Sudoku puzzles.
Sounds fascinating, but why did you say graph coloring?
Because this is what the 4-color theorem is about. The theorem is stated for coloring in graphs.
What type of graphs?
A graph is an object consisting of 2 sets called vertices and edges. The vertices are also called nodes, dots, or points, and the alternative names of edges are arcs, links, or lines.
So, the edges are used to connect pairs of vertices.
Exactly. And we call such pairs of vertices adjacent or neighbors.
Looks like the same thing as a network to me.
Yes, these two terms are synonymous, with a graph essentially being a mathematical abstraction of a network. So, a network is a more broad term that can be used in various contexts.
Such as social networks, telecommunication networks, transportation networks, right?
Yes, graphs and networks are very useful for modeling many real-life situations.
Who was the first to come up with such a wonderful idea? Perhaps ancient Greeks.
You would think so, but in reality the origins of graph theory are attributed to Euler, who used a graph to solve the Königsberg Bridge problem in 1736.
What's the Königsberg Bridge problem?
The city of Königsberg in 18th century Prussia was split into 4 parts by Pragal River. These 4 parts were connected by 7 bridges shown in red in the figure.
I see that the graph representation is built by using nodes for the land parts and edges for the bridges, right?
This is correct.
I guess Euler was looking for an optimal tour between the parts.
Kinda. He was looking for a tour that would start in one of the parts, visit all 7 bridges exactly once, and return to the original location.
Why do you say kinda then? Sounds like a tour to me, like the one we built to solve the Lonely Night puzzle, isn't it?
Not exactly. In the Lonely Night puzzle and in the traveling salesman problem, we are looking for a tour that visits every node once. This is called a Hamiltonian tour. And here we are looking for a tour that visits every edge once, and each node can be visited multiple times.
Okay, you are right, I'm less right. Does such a tour have a name?
Yes, it is called an Eulerian tour.
Makes sense. I would imagine that the number of edges is larger than the number of nodes in most cases. Is finding a Eulerian tour even harder than finding a Hamiltonian tour then?
It is actually the opposite. A Eulerian tour is easy to find whenever one exists. In fact, we can prove that a Eulerian tour exists if and only if the degree of every node in the graph is even.
I can see why. You need to be able to leave a node every time you enter it.
Right, with the exception of the node you start at. But in that case you need to return to it, so the degree of the starting node must also be even.
For example, since there are nodes of odd degree in the Königsberg graph, it has no Eulerian tour. But if we adjust 2 edges shown in green, all degrees become even and we can easily find a Eulerian tour.
That's a great example, Max.
Cool. Now, can you finally tell me about graph coloring?
Sure. To obtain a proper vertex coloring, we need to assign colors to all the vertices so that no 2 adjacent vertices have the same color.
Now I see the map coloring connection. You represent each state by a node and build an edge between 2 nodes if the corresponding states have a common border.
Right. And in the minimum vertex coloring problem, we need to find a minimum number of different colors required to color the graph properly. This minimum number is called the chromatic number of the graph.
Okay, this is a reasonable definition, but I don't see how the 4-color theorem can be correct. I can easily draw graphs that require more than 4 colors for a proper coloring. Look at this graph for example. Since all possible edges are present, I have to use a different color for every vertex, so I need 5 colors.
Yes, you do. Your graph is complete because it has no missing edges. The set of vertices of such a graph is called a clique.
Like in a high school clique.
Exactly.
I hated those.
Me too, but I love looking for maximum cliques in graphs, it's fun. And it helps with coloring, because whenever you find a clique with k vertices in your graph, this means that you need at least k colors for a proper coloring.
That's exactly what I'm saying. You need a new color for each vertex in a clique. So, how can you claim that 4 colors will always be enough?
Well, not always, but 4 colors are always enough for coloring any graph that is planar.
What is planar?
A graph is planar if and only if it can be drawn on the plane so that its edges don't intersect. Clearly, a complete graph on 5 vertices is not planar, because there is no way you can draw its edges so that they don't intersect.
Indeed. So, the 4-color theorem doesn't apply to this graph.
Correct. But it does apply to a clique on 4 vertices.
I can see that. It is easy to draw without any edge intersections. I wonder if the 4-color theorem is easy to prove.
It does look simple, but the only proofs we have to date rely on computer software. There is still no simple mathematical proof, despite many attempts over the past couple of centuries. Maybe you can do it?
LOL. Very funny. So, how do we use graph coloring to solve Sudoku?
It's actually pretty simple. You just need to construct a suitable graph, where a proper coloring will correspond to a Sudoku solution.
Let me think. I think I got it. We create a vertex for each Sudoku cell, so there will be 81 vertex. Then we draw an edge between each pair of cells that cannot be assigned the same number in Sudoku.
I assume that the colored vertices correspond to the cells with given numbers in the puzzle.
Right. And I only illustrated the edges for a corner vertex and for a vertex in the middle. I was too lazy to draw all the edges.
Naturally, the vertices in the same block or row, or column form a clique on 9 vertices.
So, we need at least 9 colors for a proper coloring, and an optimal coloring will achieve this lower bound.
You are a genius, Max.
I am not sure about that, but I do have a good music taste.
That Sudoku song is still stuck in my head.
That's what I'm talking about. Show must go on.